Today I'm here to talk to you about the Android operating system and what is actually managing our application. So the first thing that people usually talk about when they talk about Android is they're saying Android is Linux or Android is based on Linux. And Linux is an open source operating system that works on computers. And Android took a lot from it and is based on it. It took stuff like the kernel and a lot of the core concepts that Linux uses and uses them on Android as well. But it's not purely just another flavor of Linux or another Linux distribution. It's really only based on it and made some extensive changes. Most of them are based on the fact that it's an operating system made for phones and not for computers. And I will also briefly mention this concept later in the talk in various phases. I will say this is a concept from Linux, or this is a modification that was made for Android. And we're going to cover the basic Android architecture in this talk. And we're going to work our way from bottom to top and cover the kernel, the init process, some processes that are important to us as developers, the system server, and on the top is our applications, our Android applications. So starting from the bottom and talking about the kernel. So what is a kernel? The kernel is a computer program that is the core of a computer's operating system. It has complete control over everything in the system. It's the first program to start up, and it handles the rest of the startup. It handles input-output from other software or other hardware. It handles CPUs and memory allocations. And the basic definition of a process is that the process is an instance of a computer program that is being executed. So let's talk a little bit more about the Android kernel. The Android kernel is built on the Linux kernel, which means that it does a lot of the things exactly the same. It really just copies the Linux kernel. It does the memory management the same way, CPU management the same way. Things like, again, hardware and software requests similarly. And there are some modifications that were made on top of the Linux kernel to make it more better suited for Android and better suited for phones instead of computers. The reason that Android is using the Linux kernel is that it works. It works on computers and it works well. It has proven models for both the, like I said, the memory management and the process management and the CPU management. It has a permission-based security model that is, again, tested and has been working on computers for many, many years. And it's open source, so it's easy to contribute to and take from. So Android has done a few modifications to the kernel to, again, make it more suited for phones. And I'm going to mention two that I thought were the most important ones. And the first one that I'm going to talk about is the out-of-memory killer. The out-of-memory killer is based on the fact that on a phone needs to always be responsive because it needs to get events, get phone calls, get messages, and things like that. And users don't explicitly close applications. Like, they don't be like, okay, I'm done with this app and I'm gonna go and swipe it away. Also, phones typically have less memory and less tricks to use sort of fake memory than computers. So one of the biggest modifications that Android done was being more proactive about deciding by itself when and what processes to kill in order to make sure that we never reach a critical out-of-memory level. We never reach a point where Android wants to allocate more memory and there is no memory to allocate. So all processes are ranked according to importance, And every time the kernel reaches a certain threshold, a certain watermark, it basically goes like, oh, hey, I need to clear out some memory. This is way before we, like I said, run out of memory. It's some earlier stages. And then it just clears out as many processes that are ranked as not important until it clears enough memory to be, okay, now this threshold has been met. In this example, I'm showing a list of processes that I pulled off my phone. In this case, it's 30 total processes. And what I did next was I opened up my camera and started taking a bunch of pictures, which is a very intensive operation. And I didn't do anything else, and the out-of-memory killer kicked in and killed a bunch of processes for me. And it did that so I can continue taking pictures and doing whatever I needed to do without running into memory issues. The second modification that Android made to the kernel is the wake locks. And the wake locks are meant to guarantee that our phone uses as little battery as possible and stays awake as little as possible. And that would give the processes, they would use less energy and be able to sleep more. And the wake locks basically mean if there are no wake locks, put the CPU into a dormant state where they can still be woken up by certain calls, but it's not working at full capacity. And again, using less memory. So this is what we would normally see if we would query how many wake locks our phone has at a certain point of time, with maybe like little peaks when a new screen is drawn or when a network request is being made. But these are like really, really tiny. And then it would go back to 0. If there is an ongoing thing happening on our phone, such as playing a video, we would see that now we have 2 wake locks that are being held. One, in this case, because it's video, so one is for the screen and one is for the audio. And like I said, there are a bunch more modifications that are made to the kernel. I'm not going to cover them now, but these are, like I said, what I think are the most important ones. And the next part that I want to talk about is the init process. So the init process is a binary that's picked up by the kernel and is being run on startup. And it has a list of settings and a list of instructions, a list of definitions to startup processes. And it wakes up all the other parts of the operating system. So it runs on startup, and it's the first user space process. It is also the root of all other processes. They all created from init. And like I said, it spawns everything else. Some of the processes that it starts, we know, we recognize, such as ADBD and logd and installD and zygote. These are all daemons, which means that they run as a background process. The user doesn't have an interaction with them. They will not know they exist. They will be restarted in case they, for some reason, crash or die. And they just run in the background throughout the life of the phone, the operating, as long as it's working. I drew a bigger circle around zygote because it's the thing I'm going to talk about next, and the more important for us, more important daemon. So what is zygote? Zygote is the base of all other applications. It was designed to share and save memory and reduce app startup time. And what we basically see here is that zygote is a runtime environment that's ready to just start running an app. Our apps run inside of a runtime managed environment, which is Dalvik or R, depends on our phone, depends on the version. And if we were to create a brand new runtime environment for every app that we start, we would waste a lot of time just creating this from scratch. So zygote is sort of a shortcut in a way. It's a process that's really just sitting there, all set up and ready to run our Java code, our Kotlin code. It has, like I said, the runtime environment, preloaded resources, preloaded classes that can be used later to run any app. So in order to create a new process on Linux, Linux usually uses two commands. One of them is fork, which means take a parent process and clone it, make an identical child process from it. And the second phase is called exec. And exec is on the child process that you just created, delete all of the previous code that was, all the previous memory that was there, and just start from scratch. Give me something new to run on this brand new created process. Zygote, when it's creating apps, it's being forked, which means we get an identical copy of the parent, but it's not being exact, which means the memory, whatever's in it, is not being deleted, which is again perfect for us when we want to start a new app, because now we can say, hey, Zygote, please fork this process, fork yourself, and run our app in it. Everything is already there. We don't need to delete it. We have the runtime environment, we have the shared resources, we have the shared classes. And if we wanted, again, to create another app, a second app, a third app, a fourth app, again, we would go back to Zygote and say, fork, but not exec. Again, we will have multiple copies of Zygote running different applications in different processes, running different code, different Java code or different Kotlin code. This also helps with memory management because Zygote and the runtime environment have classes that are shared between them and combined between them. So again, we can initialize them only once and we don't have to initialize them again and again. And this is something that everyone would see when they get exceptions. If you dive deep enough into the code base, you would end up seeing some sort of reference to the Zygote, because at some point we will reach some code that was initialized there or was run there. Now, usually in Linux, apps run under the same user. And user is me or you or an admin. And processes that run in this manner have permissions to sometimes share files, share memory, and things like that. And Android decided to create a stricter model about processes and user IDs. And what they basically said was, we'll use Linux user IDs, but we'll say that every app, that basically every process, is its own user. We'll give every app, every process, a unique user ID, and that way every app will not be able to share memory or corrupt files or touch other processes' files or memory, and that way processes will be more secure and still use Linux features about security, but change it in a way that suited Android. And again, this is a list of processes that I pulled off my phone. The left row is the process ID, and it's all different. So again, they cannot be sharing things between them. The next thing I want to talk about is the binder IPC. I just spoke a little bit about how processes have their own user IDs and how they actually can't communicate with each other. And then the next question is, but we often do. We sometimes have to ask some other process to do things for us, or we just want to maybe transmit some information, and we need a way for processes to communicate and to do that. And the mechanism to do that in Android is called the binder IPC. And I pulled up these 3 lines that I think many Android developers saw, or other variations of it. In this case, I am contacting something called connectivity manager. It's not sitting in my app, it's somewhere else. And I'm telling it, get me that system service, get me that other process, and ask it, what is the active network info? What is really happening with, in this case, with the network right now? But I could make any number of requests on many other processes. The reason why I am asking this from someone else and not actually writing this code in my app, or why this code isn't being pulled into my app instance, is that in order, for example, in this case, to ask about network info, that process needs permissions to talk to drivers, to talk to hardware, to ask hardware questions like, am I on Wi-Fi, and things like that. And that would make my app needing more permissions and less secure. So by putting this method somewhere else in another process, that other process has these permissions, and I don't need them. So if I go and travel to the source of my get active network info, this is what I'll see. I'll see an interface, an iConnectivity Manager member, and all my methods are getting called on this member. I don't really see the implementation of the actual call. I don't really see the code of what is happening inside this call. And if I have AOSP and I search for this interface, again, this is what I see. I see just a simple interface with like methods, but I don't again see the implementation of them. I don't see it in my code and not there. And then the question is, of course, why? And the answer would be because, like I said, we are not actually talking directly to that other process. We're not really asking it directly for things. We are going through the binder mechanism, which looks like that. If we go from app 1, we go all the way down to the kernel and then back up to the other app to send and receive messages. So I'm going to go over each and every component. And the very basic one, again, where everything happens, is the kernel, the binder modal in the kernel. It is the only thing that actually knows about the other process. None of the arrows in my previous slide was speaking directly with app 1 with app 2. Kernel is where the transition itself is happening, the transmission itself is happening. And the kernel serves as the mailman in this example. It knows how to, it keeps reference to all the processes that are being contacted and from where. It keeps being aware of their existence, whether they're there or not, and to deliver the right message to the right object. So the way that the kernel is getting and submitting messages is through system calls. But we are not writing system calls and we're not writing kernel code, we're writing Java. So there is a class in Java that is creating our message and calling that particular system call. It's called the binder, and it has two main methods. The transact is the thing sending the message, and the onTransact is what will get invoked when you receive the message and open it up. Now, I'm talking about messages, which is a little bit confusing because we're not really sending a message. We're not saying, hey, I hope you're good. The weather here is fine. I'm saying, I want you to execute a function for me. I want you to call a method on your on your side. I want to ask you a question, and I want to get an answer back. So this part of creating a message that will later be opened up and be translated into, oh, you meant to call this particular method. This is what is being done by the method transact. Will take the, oh, you meant to call this method with these parameters, turn it into something called a parcel. And the onTransact will open up this parcel and say, oh, this parcel means you wanted to call this method. I will do that and give you back the answer. Now, again, if we were to look at this code, it's in Java, but I mean, if we were to spend our lives creating parcels and figuring out how the other side wanted them to be opened up and creating all this like complex extraction, and we would just be writing very tedious and very boilerplate code. So that's why we have the AIDL tool that is actually the tool that will create the bridge between the actual methods and the transaction calls. And it will generate two parts: proxy on the sender side and the stub on the recipient side. So on the proxy side, it would look like that. Whenever we want to call this method, get activity network, we would create some sort of parcel, put information in it. This is, if you can see clearly, the class that is named data. We create the parcel with the data and with the reply. And in the middle there, we will call transact, which will call the system call and actually transmit our request. And on the other side, we would see the stub. The stub overwrites on transact. It would open up this parcel, say, oh, what you wanted to do is you wanted to call this method get active network, and it would do that thing. This is the actual concrete implementation, in this case, of this method. So if we go to this get active network, this is what we'll see, which is the actual code, the actual implementation of this particular method. And if we go back to our original request, which was connectivity manager get active network info, and we would debug it and see what is sitting there underneath the hood in our connectivity manager, we will see that it's the iConnectivity manager proxy class. So to wrap it all up, this is how it would look like with the actual calls. App 1 would call some interface in App 2's method, some method. Our Java interface classes, our AIDL, will translate that into parcels and call transact. And it will call transact on the binder. The binder will then call a system call to the kernel. The kernel will figure out who is our recipient, who are we sending this message to, and will do that, actually send a message. It will send back a system call to app2's binder class. The method that will get invoked is the onTransact. OnTransact will figure out, open up the parcel, will figure out what actual method we wanted to call on app2's actual object and call the actual method. The last bit of the operating system that I want to talk about is the system server. The system server is also initialized by init, and it is forked from Zygote. So it is also a Java application. It is the heart and the core of all Android. It manages all the Android apps, and I'll talk a little bit more about that in a little bit. And it manages things like location, like power, like Wi-Fi. It has modular functionality. It's split into managers, little managers inside, but it is one big process. And it is one of the more core important processes for any Android apps to run. And there are many, many managers in the system server. And I focused on 3 that are most important to us, I think, as developers, which are the Activity Manager and the Windows Manager and Package Manager. So the Windows Manager is the one responsible for our windows and for what is being drawn on the screen by our apps, by our activities, fragments, views, etc. Its responsibilities include things like keeping track of the window activities, what is being shown, what is being invisible, transitioning between them, giving the user in general a good UI experience, which means that it cheats a little bit sometimes. For example, it will take screenshots and display them in certain cases when it's transitioning between one thing to another. And it's also handling the system level gestures, which means that if we didn't handle a certain click or a certain other UI gesture and it bubbled up until it reaches the window manager, it will decide what to do on top of it. Another important manager is the package manager. The package manager is the thing that is responsible for looking at our manifest files and doing things like installing new applications and resolving the correct activity when we are looking for a certain activity. And on startup, it goes through all the manifest files in our Android phone, and it creates a huge list in memory of all activities and all like possible intents in all the phone, basically in all our apps. And what it also gives us, if we ask for an activity, we say we want to start a new activity, what can we do? Is this if this is an implicit activity and we can maybe instantiate more than one type of activity that fits this criteria, it can create us that list give us all the activities that can actually match this filter, match this intent. And the last manager that I wanted to talk about is the activities manager. The activities manager is the heart of maybe everything. It's the most important manager. And it's responsible for managing applications. So all our applications are being managed by it. Every time a new activity starts, pauses, resumes, everything, it will be the one deciding that that thing has happened and creating activities if needed, destroying activities if needed. It's managing all the lifecycle events. It's managing the actual user, that is whoever's using that phone at that point. It is responsible for memory trimming. It is responsible for killing off rogue activities that are taking too much memory and handling configuration changes. So when we're talking about managing applications, the activity manager will pile up our applications into some data structures. And the data structure that it uses is it will put a stack. There can be one or more stacks. For example, in case of a split screen, there will be 2 stacks. Inside the stacks, there will be tasks, and a task correlates to mostly one process, and rare occasions more than one. And inside a task, there can be 1 or more activities. So I talked about processes up until now, but we're not writing processes, we're writing activities. And how do they correlate with each other? How do activities live inside processes? So for every activity that's created, Activity Manager will create an activity record, which is just a data structure that is there to keep track of this activity, where it is, what state it is, what window it has, etc. And in this case, it's really simple. We have one task, and in it, one activity record. And this task, this activity record, correlates to one activity that's living in one process. If we were to create, for this app, a second activity, we would navigate from activity 1 to activity 2. A second activity record would be created in our task. And a second activity will be created in our app process. So again, fairly simple. If, again, another app would be started, then another task would be started, another activity record would be in it, and another process would be started for it. So we would have one process holding one activity, and then another process holding our other two activities. And the last bit is where it gets confusing. Because say I navigated from my app's activity to another app's activity. A very clear example is in the case of sharing. I opened up my share screen and I wanted to open another app in order to share my content through the other app. We would get, in this case, another app's task. We would get in our app's task, we would get the other activity record. But the process would be the other process. So in our task would be one activity that sort of belonged to the original application and another activity that belongs to another application. So they would live in the same task, but they would not live in the same process. So when Activity Manager manages the lifecycle, there are a few things that it does. For example, so the main top thing that it does is it only makes sure that there's only one resumed app at all time. There's every time, even if we see 3 apps on the screen, even on split screen, even on picture-in-picture, there's always only one resumed app. It will pause, stop every other activity. It is also responsible to deciding which activity has a surface, is visible, will communicate that back to the window manager. It's deciding things like thread priority and CPU affinity, which is apps that are running right now or apps that are in the forefront will get more resources to run than other apps. It will give and take away certain permissions from apps. If our app is stopped, it cannot do certain things. And it will make the out-of-memory adjustments, which is a topic that I'm going to cover right now. If we go back to when I talked about the kernel and I said that every process has an out-of-memory score. And that out-of-memory score is based on how important the process is. And how important a process is not something the kernel would know, because the kernel has no idea about things such as what is an activity or what is the actual activity that is resumed right now, what activities are not resumed right now. The kernel just doesn't know it, and the thing that knows it is the activity manager, because it manages all these adjustments. So Activity Manager is responsible for deciding and giving every process an out-of-memory score that later will be used by the kernel to decide which processes to kill. So again, if we're looking at the list of processes that are also conveniently sorted from most important to least important, we can see that there are different categories in which they are sorted by. And the top most important one is the system server. The second 3 are persistent. Then we go to the foreground, which is the process, the application, the activity that is actually being used by the user at this point. Then it's visible, maybe things that are partially visible, or if we have some foreground services. Perceivable, and on, and I didn't put in the rest of them, but I think that kind of shows the point. And inside Activity Manager, there are 2 methods that will be applied and compute the out-of-memory score every time anything changes, really. Anytime an activity is being started, stopped, resumed, created, stopped, user started a service, anything like that. These methods will get called. They will run through all the processes and give them a current score. Activity, in case the kernel actually woke up and killed a bunch of processes, it will also let Activity Manager Service know, and it will remove these activity records and remove all the redundant information because these processes are no longer there and there's nothing left. To wrap up this talk, I wanted to go through the process of starting a new activity and show you a little bit of how it looks like in the Activity Manager Service and show you a little bit of the other concepts that I talked about here. So I'm picking a path that will show you the most of these things. There are many paths that can create a new activity. You can, for example, already have a process to run this activity in. You can actually find out that this activity was used before and you don't need to create it and things like that. So I chose the most everything is new path. And in Activity Manager Service, we will see methods that are pretty straightforward. Start activity as user, which will call something internal that is called start activity may wait. And in it, the first thing we'll do is we'll resolve the intent. And this will call the package manager and ask the package manager service, hey, please give me all the activities that match my criteria, that match either my name or can perform a certain action. And the resolve intent will go and be like, okay, I will give you the correct list or the correct single activity. In this case, we're going with a single activity. So we will get activity info with the one activity that we wanted to create. A new activity record inside Activity Manager Service will be created with all the information about this activity. I put a generic example of how throughout this path, Activity Manager Service will talk to Window Manager Service and do things such as create our window, create a transaction between whatever was showing before to our new activity. And now that our activity record is ready and our activity is ready to be actually shown and created, we will create it and resume it at the same time. So now we are actually deciding if we already have a process to use. And if not, we'll also create a record for our process called process record. If we do not have a process, we would start a new one, and we would call process start. And in process start, we will see that we are actually creating a new fork from Zygote. So this is the Zygote call to, hey, please fork yourself, and let us know let us know when you're ready. Let us know when a new process was created and ready to run our activity, run our app. And again, in Activity Manager Service, when the Zygote calls back, it will say, hey, I got this, I'm ready, what to do? Then we will bind the new application to it. All right, that's it. Thank you so much for coming. Yeah, I can take questions, or you can also come over later if you want.
Very good talk, really informative too. I know there's a lot of constraints with using a lot of legacy code. Is there a part of the architecture that stands out as something you would change if it were being rewritten today from scratch?
Good question. It's not just because of legacy code. I think one thing I found out that there's a lot of edge cases that we as developers aren't even aware of or don't even think about, which make this whole tree very complicated. I don't know if that's really changeable because, like, really, there's a lot of edge cases a lot of things that can go wrong in the middle, a lot of things that can be, I don't know, really exceptions to this very simple path that I showed. I showed it in a very, like, this is like super simple, but I skipped like maybe hundreds and hundreds of if cases and
What exactly resides in the preloaded resources, which is inside the zygote? There was one section which you showed, say you have a zygote, and inside zygote we have a Dalvik and a preloaded resources. So are the preloaded resources, like when do they get preloaded? When my app is installed, or?
These are not your app's resources. These are generic resources that are shared between all apps and shared between all processes that will be forked from Zygote. Your app's specific resources will only be loaded once your particular app is running inside an instance that was forked from Zygote.
Okay, thank you.